Welcome to Economics Korea. It is a well-known fact that Korea's natural energy resources are extremely limited. Yet largely because of its dramatic success in economic development, Korea's growth in the amount of energy used has been the fastest among the OECD economies. And to address this issue, Korea has been working to transform its economy with a goal to make it one of the world's most energy-efficient ones in the future. And in today's edition of this program, Economics Korea, we will look into one of the places where frontline efforts are being made. That is designing and building zero-energy waste buildings. But first, we'll begin the program with the fascinating world of biomimetics. It is an approach in technology innovation that finds solutions by looking into how living life forms work and applying these findings into mechanical engineering. From robotics, through medical product designs, and all the way to avionics, the scope of application is largely unlimited. And our EK Plus report here will explain how Korea has been fast moving up from the position of a learner to that of a global leader in this high-tech field. Let's take a look.
We cannot imagine how mysterious nature's viability is. When we are impressed by the nature's greatness, there are the people who's asking why, and this question motivates the biomimetics. Today, let's look at Korean biomimetics, which is one of the leading technologies in the world.
The greatest swimmer of the modern era.
Australian swimmer Ian Thorpe won 3 gold medals in the 2000 Sydney Olympics. With his amazing performance, his full-body swimsuit drew global attention. The design inspiration for this innovation are sharks. Shark skin helps it swim faster, and so that function was duplicated. Throughout history, we've benefited greatly from biomimetic engineering.
I'm here to see the new adhesive tapes developed by Lizard Characteristics. So let's go in and check the secret technologies.
At this lab, the team is busy studying geckos. Geckos climb any surface with ease using millions of micron-scale adhesive foot hairs on each toe. Each foot hair splits into hundreds of tips only 200 nanometers in diameter. A single gecko foot hair is 100 millionth of a meter long. Each strand ends in up to 1,000 even tinier tips. The tips are only 200 billionth of a meter wide. That's below the wavelength of visible light.
이게 개코도마뱀 발바닥인가 봐요.
예, 그렇죠.
예, 어떤 특성이 있길래 이걸 접착제까지 발견하셨어요?
이런 아주 미세한 손모가 실제로 분자간의 인력, 그 힘에 의해서 이렇게 달라붙는 게 관찰이 되었고, 그래서 저희는 이제 이런 것들을 공학적으로 응용을 해서 이런 미세한 손모를 제가 가지고 있는 이제 나노 기술을 이용해서 구현을 해서 이런 성능을 넘어설 수 있는 접착 배치를 개발하려고 노력을 많이 하고 있습니다.
The microadhesive permits intimate contact with rough and smooth surfaces alike. Using this principle, Professor Saw developed a similar artificial adhesive. Delicate engraving skills are required to create the man-made gecko foot hair. After making a mold using nanotechnology, the right mix of ingredients are poured into it. The solidified mixture is the final product. Professor Saw's team succeeded in creating this revolutionary product finer than the finest human hair. This artificial product is useful in transferring solar panels, displays, or semiconductors. Using other tools can cause troubles like static electricity and can leave residues. But the nanohair's adhesive microstructure leaves no residue and detaches without measurable forces.
개코도마뱀을 이용한 그 접착 테이프가 붙여 있는 건가요?
예, 그 기존의 접착제랑 다르게 그 나노 헤어들이 존재하는 이 테이프에 청정하게 그 웨이퍼를 움직일 수 있는 그런 시스템입니다. 예, 가볍게 붙이게 되면 크게 힘 가하지도 않고 접착이 이루어지고 그리고 다시 이렇게 되고 그 다음에 이것을 가볍게 띄었을 때 이제 표면에 어떤 큰 무리가 가지 않는다, 그리고 오염이 되지 않는다는 걸 볼 수 있습니다.
예, 처음 상태대로 진짜 그 아무것도 묻지 않고 표면에 깨끗한 상태가 유지됐네요.
네.
The hair is perfect for band-aids. It's dry and needs no other adhesives unlike conventional band-aids. It sticks to skin well without causing irritation, and it can be reused many times.
We are trying to develop products that can make use of our technologies. We will coordinate with display and semiconductor companies to upgrade our technology further. We are planning to create marketable products using our technology in 3 years' time.
During the 15th century, Leonardo da Vinci studied animals and insects of flight to develop flying machines. Similar studies on insects are carried out in Korea. A team of researchers in Konkuk University is developing miniature flying machines. How small? 15 centimeters long and less than 100 grams in weight.
This is our mini flying machine, designed after the dynastid beetle. Dynastid beetles are bigger than most insects, so they were easier to work with. They have retractable wings, and that gave us the idea to create this flying machine. If we can imitate this quality, we'll be able to develop a portable flying machine.
The simple movements of the insect's wings are something to marvel at. The beetle's wings flap more than 30 times per second while covering a 180-degree angle. It uses the energy created from a vortex of air to fly instead of relying on simple aerodynamics. This machine tries to duplicate that function. So far, the machine's wing flaps around 40 times per second. The team continually made upgrades to the wing movement. Various tests were carried out using different boosters and weights as well. All these experiments helped the team decide how the weight of batteries and other parts might affect the machine's performance.
We developed this method to measure the thrust produced by a flapping wing system. If it can rotate around 360 degrees, it means that it can generate large thrust and it overcome the weight of the flapping wing system. It not rotates 360 degrees. It means that the thrust smaller than the weight, but we can calculate the thrust by making the formulas from that angle. Yeah.
Insects maintain stability while in flight without tail wings. Studies to mimic this ability is ongoing as well. Flying with wings retracted like beetles is also another challenge. Such breakthroughs promise endless possibilities.
Levitating a vehicle alone requires a lot of energy. Our solution to more efficient energy travel was simple. Jumping from one place to another and using the wings to jump higher and further. We are studying this mechanism intensively so that we can create robots that imitate what grasshoppers can do.
To survive, nature forced various species to evolve. We will always have something to learn from them. By studying their efficiency in achieving various tasks, mankind can develop new technologies that can help them reach the next level.